Geisberg with Lab Group 3A. This is Lab 5 for spherical aberration. So really quickly I'm going to talk about how we set our stuff up and what was necessary to make it work and kind of the problems we ran into. So for this lab it's a little bit different than our first 4 labs. We have our laser here aligned with our primary rail, which is now along the side axis of the table instead of down the length. We have a flat mirror here, and what this mirror is doing is sending our beam straight down the secondary optical rail. So here we have a pinhole, and we use this pinhole initially to block the outer filters, the outer light, as we were going through the center hole on our Hartmann mask. And our Hartmann mask is the 11 pinhole array that goes parallel to the surface of the table. It's very important that it's parallel because all the movements that we're making are along the plane of the table. So our mirror, our laser, our lens, and our microscope all have the ability to laterally translate with a micrometer. And it's very important because we need to make fine-tuned adjustments. And our lens and our Hartmann mask and our mirror are all on tip-tilt adjustment, and our microscope is as well. So this is a very accurate lab. Some of the problems we ran into, the micrometers on both our mirror and our microscope, actually when we were moving them, capped out. They weren't long enough for some of the measurements we were taking. So we had to realign, I think 3 times during the lab. So it took a lot longer than it should have. But once we got to a good spot, we were able to move both longitudinally and laterally with our microscope to measure both longitudinal and transverse aberration. And then physically what we see when we are looking for the marginal focus is we move through the different edges. We use our Hartmann mask and we move through the edge, through the line of the lens to the different parts. And we started on the edge of the lens, and that's the part of the lens that we're going to see the most spherical aberration because there's the most curvature. And our microscope, we started at that position, and as we moved our mirror and translated across the Hartmann mask and across the lens, our microscope translated the most when we just moved a little bit, the first couple holes. And then when we went back towards marginal focus, the center hole, the microscope went back to the center where we started. And as we kept going, it actually moved closer. And then when we went back to the other extreme, the last hole, it went back to where it started. So the extremes were both at the same focus, and the center was at that same focus because the center is going straight down the line of the system. So all 3 of those points were at the same, but we saw the most deviation with our spherical aberration when we just moved 1 or 2 holes with the Hartmann mask.
Hi, I'm Garrett. I'm also part of Group 3A, and I'll sort of talk you through how we measured the spherical aberration for this particular lens. We essentially took 2 different measurements, measuring the transverse ray error and the longitudinal spherical aberration. So for the first setup, as Ryan described, we simply translated the mirror and got the laser to go through each hole in the Hartmann mask, keeping all of these still, and we only moved the microscope laterally to bring it back into focus on the crosshair on the original spot. So we measure mirror position, which directly correlates to the hole position and the laser position on the pupil. And we also measure the microscope position, and then we'll plot those 2. And then for longitudinal, it's the exact same setup. You bring it back to marginal focus, which is when the laser is at going through one of these extreme holes and the microscope is in focus. And then you don't touch the translation or the lateral translation. And then you scan the beam through again, just like before, and you move the microscope longitudinally, as Ryan previously described, each time centering the laser back on the original spot of focus. Since the lens we used was plano convex, we have 2 shape factors available, +1 and -1. And as theory sort of predicts, the positive 1 shape factor gives much less spherical aberration. This goes from -0.5 to about 0.4, whereas this is about 10 times more, from -4 to 4 millimeters. What happens in the major difference between these 2 plots is it looks like there's a little bit of defocus because you can see that there's a different slope at the origin. for each of the two cases, but otherwise the spherical aberration is generally the same and has the same slopes at the edge of the field.
Alright, and Garrett just went over the graphs that we got for our spherical aberration, and I'm going to kind of run through the equation and show you what we have here. So RP is the radius of our entrance pupil, which is ½ an inch, and then the power of the lens is 0.01 inverse millimeters, and then NO is the index of the atmosphere or the surrounding environment, which is air, which is 1. And then we run through this whole equation here, very, very long. We say our object is at infinity, so we know C here and here is going to be -1, and then we know N for the KPX 094 lens is BK7 glass, so the index is 1.517. We say that as spherical aberration increases, our shape factor is going to go down, and that is confirmed by our lab data. And to find the minimum spherical aberration, we said B equal to the negative of this equation right here, and we found that to be 0.74. Also, for a collimation lens, we have a shape factor of -1 here, and then a shape factor of 1 here. We found that for minimum spherical aberration, we had a shape factor of +1. And that was pretty much the end of the lab, and thank you.